Hello students, so today I will explain the structural elucidation of one of the another terpenoid, that is α-Terpineol. In my previous lectures I told you the structural elucidation and synthesis of citral and geraniol. So let's explain the structural elucidation of α-Terpineol. So the structure that we have to determine is this. This is the structure that we have to determine. This is the structure of α-Terpineol and it was determined by Velage. It was determined in Velage in early of 1900 and 1905 or something like this. So it was determined by Velage. Now, first of all, its molecular formula was determined, and the molecular formula that can be determined by the elemental analysis. Its molecular formula was determined to be C10H18O. So if we count the number of hydrogen, carbon and oxygen, then it is C10H18O. Okay, it means this is a terpenoid, not the terpene. One of the oxygen is present over here, and as this is one of the monoterpenoid. If 10 carbon atom are present, it means it is a monoterpenoid, and we can see here by this structure it is a cyclic monoterpenoid. It is a cyclic monoterpenoid in which the two isoprene units are joined by head to tail. So these are the two isoprene units. So this is the tail part and this is the head part. If we see, then this is the tail part, and then if I draw it in this way, then this is the head part, this is the head part, and this is our tail part of these two isoprene units. So these are joined in this fashion. So this is tail part and this is the head part. Okay. Now, so after that, second, it was after determining this molecular formula, it's a double bond equivalent that was determined. So double bond equivalent means number of carbon atom minus number of hydrogen atom, that is monovalent atom, divided by 2. Number of, there is no trivalent atom like nitrogen, that's why we can write trivalent atom is 0 divided by 2. Number of trivalent atom is 0 plus 1. Okay, so this comes out to be 2. 2 means there may be 2 double bond. I have already written the structure, that's why we see that one double bond is present. Otherwise we may presume that 2 double bonds may be present, or 2 rings may be present, or combination of double bond or ring that may be equal to 2. Okay, but here we can see that means which is followed, this double bond plus ring, this is equal to 2. So this is the that we have to prove that here it has one double bond, one ring, that is equal to 2, dV is equal to 2. Now third thing that was realized after this means one double bond is present, and this carbon-carbon double bond that can be proved by the hydrogenation test, or it may be bromine water test can be done. So means if we have this α-Terpineol, if we have α-Terpineol, that is C10, or we can write C10H18O. So if its hydrogenation in presence of platinum or palladium is done, then it gives rise to the molecular formula C10H20O. Means 2 hydrogens are added over here. If 2 hydrogens are added, means only one double bond is present. That's why the name it is given is dihydro. dihydro alpha-terpineol. Alpha-terpineol. Okay, and another, that is, if bromine, in presence of bromine, it gave this Br2. Okay, that is dibromo alpha terpineol. It is dibromo alpha terpineol was formed. So these tests, it tells the presence of, it means therefore one double bond is present, one carbon-carbon double bond is present. We can write one carbon-carbon double bond is present. Now another test that was performed for this, the nature of oxygen, what kind of this oxygen is present, so we have to determine we have to see the nature of oxygen, and for this different tests were performed. It may be alcoholic, it may be phenolic, it may be ketonic, aldehyde, like this. So if we do the test, one of the tests that was performed, that is, suppose if alpha terpineol C10H18O alpha terpineol, if it is treated with sodium hydroxide, then it was found that this alpha terpineol that was insoluble, it is insoluble in sodium hydroxide, and we know that the phenols are soluble in NaOH. So this test, it tells that phenol, it is not phenol, means it is not phenol. Oxygen is not a phenolic form, it is not in phenolic form. Okay. Other test that was performed, that is C10H18O alpha terpineol, when it was treated with, suppose if we do the mild oxidation, if mild oxidation was done, then what was found, that it does not give the test of aldehyde and ketone. So, or we can say no aldehyde or ketone was formed. No aldehyde or ketone was formed. So what this tells, if aldehyde and ketones are not formed, then what it tells? It tells that it is neither secondary alcohol or it is neither primary alcohol. So it is neither primary or secondary alcohol, nor secondary alcohol. Okay. Now another, that is C10H18O, another test that was performed in presence of phenyl isocyanate. If the test is performed in presence of phenyl isocyanate, so this is phenyl isocyanate, then this phenyl urethane was obtained. So this is alcohol. Suppose I write it in this form, or C10H17OH. Suppose this is the alcohol. Then this the formation of phenyl urethane derivative. It tells the presence of this primary alcohol. So phenyl urethane derivative, it is a carbamate. Actually, phenyl urethane derivative, these are the carbamate. These are carbamate. So this is carbamate. Okay, this is carbamate, and this is phenyl derivative of carbamate, and here this will get C10H17O. So this is carbamate. Okay. So as I told, this carbamate are half amide and this is half ester, half amine and half ester. Okay, this is half amine, half ester. Okay, so these are the N-phenyl carbamate, N-phenyl carbamate or phenyl urethane derivative. Phenyl urethane derivative is formed. Okay. Okay. Now next test that was performed in presence of H2SO4. Suppose if we have this α-Terpineol, if α-Terpineol is there, suppose I write the structure of this α-Terpineol, then in presence of H2SO4, so what was formed? It was giving two compound. This would be protonated, and one of the compound that was obtained, that was okay, this is one of the compound that was obtained, and another compound so this is limonene. So limonene is one of the limonene, and plus this is α-Terpenoline that was obtained. α-Terpenoline was obtained. Okay, now this α-Terpenoline again in H2SO4, in presence of this H2SO4, this may undergo isomerization. Okay, in presence of H2SO4, this may undergo isomerization. So what was obtained? So after isomerization, this double bond, it may go over here. So both are the means isomers. So this double bond may go over here, and we are getting this one. Okay, so after isomerization we are getting this. Again in presence of H2SO4, so here two hydrogens are present over here. It may undergo oxidation in presence of this H2SO4, that is removal of these two hydrogen that may occur. So it may undergo oxidation, and so the driving force for this oxidation is the formation of this aromatic ring. So here this aromatic ring that will be formed. So this is this structure, we know that this is the one of the structure that is called as the parasymine. So the formation of this parasymine means our α-Terpineol has a skeleton similar to the parasymine. So what it tells? Okay, so it tells that some of the conclusion that we may draw that the α-Terpineol has parasymine type skeleton. Parasymine type skeleton means where the isopropyl group is present, is para to the methyl group. That is isopropyl in α-Terpineol also one of this isopropyl group is present para to the methyl group. This is one of the conclusion that is drawn, and other conclusion that if you see this limonene as well as this α-Terpineol, then the double bond is present over here. In both the compounds, the double bond is present over here. So it also tells the position of double bond. Okay, it tells the position of double bond also. Position of double bond. And another conclusion that we may draw, that here this OH is removed. So how we can get it? So one of the hydrogen is present over here. So this H2O may be removed. So this H2O can be removed from here also, or H2O can be removed from here also. There are two hydrogens. One hydrogen is present over here. This is one of the hydrogen. So this hydrogen can be removed, or this hydrogen can be removed. So it means the position of this OH group this OH group is present over this carbon. This is a tertiary OH group. Okay, because we are getting these two products. These two products, either the double bond is present here or double bond can be present here. So it is only possible when the OH is present at this position, when means this OH is tertiary. So it confirms the presence of tertiary alcohol group in α-Terpineol. Okay, so these are the tests. Okay, so now the presence of this double bond, the presence of a position of this double bond can also be confirmed. We know that the position of double bond are confirmed in terpenoids, and the position of double bond is confirmed by the oxidative degradation analysis. So let's do the oxidative degradation analysis for the position of final confirmation of this double bond. Position of double bond. Okay, so if you will see this position of double bond, let me rub it. So how can we confirm this double bond position? By the oxidative degradation analysis. Oxidative degradation analysis. So if we have α-Terpineol, so this is α-Terpineol, and when it was degraded in presence of means oxidative degradation, so 1% alkaline KMnO4, so it will form, first of all it will form a diol in presence of this cold alkaline KMnO4, it will form a diol. Like this. So the OH will attached over the double bond. So this diol is formed. Now further in presence of chromium oxide, this bond will break out. This bond will break, and what we may write? So we may write after breaking. So here we have OH. So suppose how the product can be written? You can write another OH over here and this OH, and this is one of the OH and this is the another OH. So after breaking we can write this OH. Now further what I told you, this H2O will get removed from here, one of the H2O will be removed from here, and after the removal of H2O, so this may be converted into this, that would be converted into keto group, and this would be converted to this, one of the hydrogen is already present over here, so this will be converted into CHO, and further oxidation that would be converted into COOH. Okay, so I can write COOH here. So this would be the product. Now in next step, or you can write it COOH. Okay, now in this is our trihydroxy compound. This is trihydroxy compound, and this is the hydroxy keto acid. This is hydroxy keto acid, and this is quite unstable. This intermediate which is formed is quite unstable, and that's why now it may undergo cyclization. So this may undergo cyclization, Okay, this may undergo cyclization. So after cyclization, what is the product which is formed? The product that is formed is something like this that we can write. Okay, so it may be written so like this. Okay, so in this way it can be written. This may be written. So this OH will be removed, and finally H2O removal. After the removal of H2O, we will get this one. Okay. So this is a cyclic ester is formed. As we can see, this is a cyclic ester which is called as a lactone. So this is a keto-lactone. So finally what we have got, keto-lactone. Keto-lactone. And this keto-lactone, again in presence of this chromium oxide, so this may break further. So it may break further. It may break further, either it may break from this place or it may break from this place. Okay. So oxidation of this keto group that will occur, this oxidation of keto, further oxidation of keto. So how further oxidation of keto? Further oxidation of this keto that can place. So we cannot break the bond from here. So according to Popoff's rule, this always the keto group goes with the smaller chain. So what is this? Keto group goes with smaller side chain. So this is the Popoff rule. Okay, so we cannot break from here. So keto group will not go with this side chain. Okay, keto group will not go with this side chain. Keto group will always go with this CH3 only. So that's why we cannot break from here. We will break from here. So here the oxidation will occur at this position. So what should be the product? This is one of the CH3, COOH. This is one of the product, and this carbon will also get oxidized. This carbon will oxidize to COH. So one of the product that is formed is, another product is CH3, COOH plus, and we are getting the another product which is okay, so COOH. So this is called as the terpenoic acid. This is called as the terpenoic acid, and further it may break further. It may undergo again oxidation of this chain may occur. Okay, here again oxidation can occur. This chain may break, and finally we may get a CO. This is called as the Carbic acid. This was called as the Carbic acid. Okay. So now, this is the position of double bond. Position of double bond, the formation of means from here to here. If we see, then the position of double bond is confirmed from here to here only, because if you see the number of carbon atom is here C10. Number of carbon atom is C10. Here also the number of carbon atom is C10. Okay, means if these rings break, why this is the position of this double bond can be confirmed because here the number of carbon atoms remain same. Suppose it is not in this cyclic ring. If double bond is not present within the cyclic ring, okay, if it is outside the cyclic ring, then we will not get the same number of carbon over here. So if the double bond is present within the same ring, then only the number of carbon atom will remain same. Okay, now suppose it means this is cyclic. One of the things that the alpha-terpineol is cyclic. Alpha-terpineol is cyclic in nature, and second, it also confirms the position of double bond. So though if it is not cyclic, suppose the alpha-terpineol is not the cyclic one, in this case if in such case if we break, in such case in case of open chain, then we will not get the same number of carbon atom. So the position of this double bond is confirmed by these studies. Okay, the further structure of alpha-terpineol that was confirmed by the synthesis of this Terpic acid and Terpenoic acid. So these two compounds that was obtained, that were found to be similar after its synthesis. So the properties of these two were found to be similar when the scientist performed its synthesis. Okay, so like as this is a monocyclic one, next that we can also do the another test, means the saturation test. If we do, if C10H18O. Okay, now if we convert this one into the saturated hydrocarbon or parent hydrocarbon, if we want to convert, because only one double bond is present in the form of carbon-carbon double bond. So if we convert this one into the saturated form, then in that case we should add 2 hydrogen. If we add 2 hydrogen to it, then this structure that would be converted into saturated form, and we will get C10H20O. And this C10H20O, the general formula for this is CnH2n minus 2. So this CnH2n minus 2, it corresponds to monocyclic terpenoid. So in this way we have proved that this alpha-terpineol contains one double bond at this position, one of the tertiary alcohol, one of the tertiary OH group at this particular position, and this is the cyclic in nature. Okay, so in this way we have proved the this was the structural study. Now final structure of alpha-terpineol that was proved after the synthesis of Terpic acid and Terpenoic acid. So let's see the synthesis of Terpic acid and Terpenoic acid. So let's see the synthesis of Terpenoic acid. Okay, so what we have to synthesize? We have to synthesize this Terpenoic acid. This is the Terpenoic acid that we have to synthesize. For this, the scientist took the reactant. The reactant that was took, that was ethyl acetoacetate. Ethyl acetoacetate was the reactant. Okay, so we can write this one in this form for our convenience, to get this structure. So I can write this one in this form. CO80, CO280. So this group is CO80, and here 2 hydrogens are present over here, 1 hydrogen, and this is the another hydrogen. Now this carbon is attached to this CO and this one. Okay, this is CO and this is methyl group. So I have written in this form. Now further what we can do, we have to bring a closer structure like this and COH over here. Okay, COH. What we do in the initially, so this was the structure in initially, and this was the structure. COOH. So the keto form was formed in this way. So in the same way we should proceed, keeping in mind this structure as well as this structure, we should proceed. Okay. So here this H group is the active hydrogen, or this is the active methylene compound. These two hydrogens are the active one. So that's why that can be removed in presence of base, strong base, that is sodium ethoxide, that can be taken out. And if we take one equivalent of sodium hydroxide, one hydrogen is removed. If two equivalent of sodium ethoxide is present, then both these two hydrogens are removed, and in this place we can add some nucleophile, that is CH2 CO2. This is ethyl chloroacetate. This is ethyl chloroacetate. So ethyl chloroacetate and two molecule of this group may be attached over here. Okay. Now, so what we will get? We will get this is our one of the this CO here, this is CH2CO2, this CH2 and CO2 ET, this is attached over here. Another CO2, this will get attached, CO2 ET, and already this group is present over here. This is CO2 ET. Okay. Now in next step what we have to do, so no doubt here if we want to get this part, then here that should be here means in presence of methyl magnesium bromide we can obtain OH group. In place of this we have to obtain OH and this methyl groups. How we can obtain? By using this methyl magnesium bromide we can obtain this part, and further we have to obtain this part also. So let's see how we can obtain this part. So first of all it can be this CO2 means ester group, it can be hydrolyzed. Ester group can be hydrolyzed, or KOH hydrolysis can be done. Okay. Now, so in next step, if we heat it, if this one is heated, then the CO2, one of the CO2 that will be removed. So in this case, after heating, only one CO2 is removed. So why? Because CO2H and CO2H. So because this COH, only this COH which is closer to this electron withdrawing group, so that's why only one COH, this COH will undergo decarboxylation, and these two COH will remain the same. Now in next step what we can do after doing it, so now what we have to get, we have to get this one of the OH over here and CH3 over here. So this can be obtained in presence of, if we react it in presence of Renard reagent CH3MgBr, then we can get one of the OH over here and CH3. But before reacting with Renard reagent, I will convert this into the ester form. So I will do the esterification, ETOH in presence of alcohol. So I will do the esterification. What is the reason for doing the esterification again? Okay, reason is that I am telling, so it would be converted into CO2ET and CO2ET ester, and this one. Now I will react it with CH3MgBr. So now I will get the product CO2ET and CO2ET over here, and this is OH. So if I perform this step, without this esterification, then in that case this acid group will also react with CH3MgBr. Okay, this acid base reaction between this H plus and this CH3 minus will get occur. This is with the nucleophile, this will get react with the H plus and CH4 that will be formed, or COMgBr that will be formed. So to prevent the reaction between this and this acid group, we should perform the esterification reaction. We should convert this acid into ester. Now we can do what we can do. We can do the hydrolysis, KOH hydrolysis now. After doing this KOH hydrolysis, what we will get? We will get the COOH again, COOH, and this. Okay, now the cyclization can occur. Cyclization will occur, and after this cyclization, we will get the terpenoic acid. We will get the terpenoic acid after cyclization. Okay, so this will be converted into lactone, and this would be five membered. This would be formed lactone. 5 membered. This cyclic ester that will be formed, and here this 2 methyl group is present over here, and at this carbon, this carbon, we have COH. So this is the structure of terpenoic acid that we have synthesized. Now let's see the synthesis of Carbic acid. Synthesis of Carbic acid. So this synthesis is easier, very easier. So if we have done the synthesis of this, similar to this, we can synthesize it. So now again we can start with the ethyl acetoacetate. So let's start with ethyl acetoacetate again, and this is H, and this is CO2ET, and I have. Okay, so in place here we have added 2 moles, 2 equivalent of sodium ethoxide and ethyl chloroacetate. So here I will add only 1 mole of sodium ethoxide and 1 mole of ethyl chloroacetate. Okay, so what we will get? One of the acidic hydrogen that would be removed, and the product that we will get here, the product that I can write is CO2ET, and here we have next CO2ET, which is present over here, C2, and this one. Clear? Now we have to again cyclization. Before the cyclization, we should convert this ester group into the COH group. So KOH hydrolysis can be done, and we can obtain COOH over here and another COH. This is another COH. Now what we will do? We have to bring OH and CH3. We have to bring OH and CH3. For this, what I have told you, we may use the Grignard reagent CH3MgBr, and further this hydrolysis, and what we will get? We will get COOH, and this is another molecule of COH. now the cyclization can occur and the removal of this H2O molecule and 5-membered ring that is formed. This is the 5-membered ring which is formed, and this 2-methyl group over here, 1 COH group over here, and this is the ketone lactone is formed. Okay, so like this is the synthesis of terpenoic acid and terpenoic acid, and this confirms the synthesis confirms the structure of α-Terpineol. Okay, thank you. So in my next lecture I will tell you the synthesis of α-Terpineol.